Well, this is just a great honor to give a lecture in Rudy's name. Yeah, so it's it's obviously been a very sad year for those of us who knew Rudy well, and I still wake up in the mornings and often think, I think about Rudy and I think, oh no, he's not here, he's not. And that's something that's difficult in an ongoing way, but we've got great memories from him. He was a postdoc with me from 2002 to 2005, as Jeloni said, and thank you for telling me about him. He was going to come to Brown because that's where I was when I talked to him and first hired him, and I had to call him up one day and say, oh, Rudy, would you mind not going to Rhode Island and coming to North Carolina instead? And he said, yeah, all right, that's okay. So luckily he hadn't rented a place, and I think he really enjoyed it in North Carolina, and it was sort of a good place for him and a good pace. There were two things that I think of about Rudy that he really enjoyed in mathematics. One of them was doing calculations. I mean, I know that sounds sort of trite because in a way that's what we all do, but Rudy would go to the coffee shop and he'd have a pad of paper and he would just sort of fill this thing out, just sheet after sheet of these calculations, and he just could do this for hours and hours, and he was really happy doing it. And the other thing is talking to other people about it. And I felt that from him, and that, I had this great opportunity to learn from him because he brought into my group something that I didn't really know and didn't really do. I might call it four-wave mixing, I guess, if I had to give it a name. But it was to do with the effect inside nonlinear systems of adding linear waves together. And but it's just remembering the kind of joy he had and the joy I had in talking with him and learning from him and hearing him and sharing mathematical ideas. So if I ever get distracted by all the other things in the academic world, that's kind of an anchor I can always bring myself back to and think about, talking with Rudy and working with him. This is actually something that is completely independent of anything I ever talked to Rudy about, or almost completely. But it was a dream of mine to get him involved in this work on data assimilation, and unfortunately it will be a dream that will not be realized, but there is one person in this who Rudy introduced me to, who's become a very important part of it. This is funded by the Office of Naval Research, and for those of you who may not know, we have a network called the Mathematics and Climate Research Network. If anybody's interested in finding out about that, let me know. We're starting to run an NSF-funded summer school in an ongoing way. We got one next month in California. Okay, so this is about assimilating data into physical models. What is data assimilation? So you have two sort of legs to science, as I think of it. You have observation, so we go out and observe the real world, and the other thing we have going for us is that we have physical laws underlying what happens in the real world. The observations give us data. When I talk about data, that's what I think of. I think of data that comes from observations. And physical laws usually are encoded in some kind of a model, right? Which you might think of as a set of differential equations like the Navier-Stokes equation in fluids or whatever. Data assimilation is about taking those two bits of information, putting them together, and coming up with some optimal estimate of the state of the system and using that as a basis for prediction. That's basically the idea of data assimilation. What I really like about it is that it treats observations and physical laws somehow equally, right? That they have this somehow this equal status, right? So it's not data driven and it's not entirely model driven either. It's sort of a balance of the two. So here's the setup we usually think of. This is the mathematical setup, and I'll explain in a minute what these different things are. But we got a state space of Rn, and we've got a model which tells us basically how to get from the state at time t to the state at time t plus 1, right? So we're thinking of sort of discrete time steps. I put a p in here because that's parameters are often very important, and part of the game is to estimate the parameters of a system. So we'll think of this as happening for values of t, like t0, t1, and so on. Okay, so advancing forward in this way, those time steps are actually characterized by the time steps at which you have observations. So the observations will also be encoded as some vectors, right? This may be some subset, this may be sort of picked off some components of this vector. Hopefully this will become clearer as time goes on, but it also may not be. There may be a complicated relationship between the y's and the x's, the state of the system and the things you actually observe. So you imagine the system is starting at x0, which is at time t0, advancing at time t1 to something, advancing then to time t2, advancing to time t3, and so on, finally up to some time tn, right? So it's a dynamical system, okay? But then, and then you end up with x of tn. But then as well, you have observations, right? Which are at each of these time steps, which are these y's here, and you want to take the information you've gotten from running the model here and from getting the observations and put it all together in some sort of systematic, logical way to get the best kind of estimate you can. Okay, so the thing that relates the two is the other important piece of the sort of mathematical setup. You've got the model, which is the sort of basic piece. The other piece, though, is the so-called observation operator, which takes you from the state of the system to the observation. So it relates the state of the system to the observations. Okay. Okay. So what are these x's? All right. So I'm interested in problems that have to do with climate, environment, atmosphere, ocean, things like this. So the x's are then generally the state variable, okay, and it's comprised of the various physical variables in the problem that you're looking at, evaluated, right, at grid points of some computational sort of grid structure, right? So you imagine this is one taken from NCAR. This is Warren Washington's, and this is sort of a grid overlaying the United States, and you can see what the grid cells look like. This is one that might have been used in a previous generation climate model. T85 indicates the resolution, right? And so you can see these grid cells. So it means in each of these grid cells, the various physical quantities would be constant, right? So you would be running a model in which you had, constant temperature, constant humidity over one of these grid cells, right? I mean, and this is, do you think about it, it's actually sort of fairly crude, right? I mean, North Carolina is probably, 5 or 6 grid cells, right? This one here is one that on the Gulf of Mexico. I'll talk about the Gulf of Mexico in a minute. This is a nice kind of curvy linear grid. This was set up by a postdoc of mine, Guillaume Vernier, who was at UNC. He now works for NOAA in Maryland, running their data assimilation scheme. And he came up with, he really liked curvilinear grids, right? So you would imagine again, you would have the physical variables be constant on each of these grid cells, and your computational model would be solving some fluid equations that would tell you how to get from one time step to another. Those time steps are not computational time steps. Those would be much finer, right? So you might do 100 computational time steps between observation time steps. This is one that I've been starting to work on Arctic sea ice, and this is one due to Pierre Rampal at the Nansen Center in Bergen, Norway, this is a model that captures the sort of open water and leads and fractures and so on, as they're called in Arctic sea ice. There's enormous interest right now in how the Arctic is breaking up and how it is going to break up in the future because of navigability of the Arctic and stuff like that. So this actually has a sort of finite element type mesh, and the interesting thing about this is that these meshes, they are evolved under the dynamics of the Arctic, and they actually get crushed, and you have to change the grid system. You have to throw away elements and introduce new elements, which is the reason we got interested in it, because that sort of challenges data assimilation. This is a picture from an IPCC report. This is now a sort of cartoon picture. You can see here, this is the world gridded up, and then the idea of the atmosphere and gridded up in many different layers. The IPCC, the International Panel on Climate Change, right? They write a report every 7 years or so. This was a previous generation one. Here you can see Britain essentially only gets one grid cell, the whole of the UK. So, of course, it's more sophisticated now. The resolution is better, but still, the resolution is still, probably 20, 30 kilometers. All right, so I think of data assimilation always in so-called sequential mode, and that's, I think, because I come from dynamical systems. So I think of it in terms of moving, as I've sort of expressed so far, from one time step to another, and then to another time step, and so on. And as I've said, what you're doing is you're putting together model and observations, and underlying it is your desire to make a prediction, but your prediction is going to be based on your best understanding of the current state of the system, and the idea is that you're continually updating that as you get information, and you're basing your prediction on the best information you have right now, right? So this is, again, another cartoon of how this works. The model runs you up to time t1, say from t0. You then make an observation. You then do an assimilation. You then update that, right? And then you sort of reinitialize, and you move on to time t2, okay? I know I'm sort of belaboring this picture a little bit, but that's because it's so sort of fundamental, and I think if you capture this, it just helps an awful lot. Right? And then you would repeat that step of observation, assimilation, update at the next time step, and then you would keep on going, right? So the question is, how does this piece work, right? What's the mathematics of this piece and this piece here, right? So at the time step, when you do the assimilation, what do you do? Okay, well, there are three different perspectives on this, and I'll explain each of those, but just to give the sort of the specs of this, actually I think it'd be worth drawing a picture here. Do you mind if I put this down for a sec? Let me just put it here. We can put it back up in a minute, but I think this has better light, doesn't it? So you're coming in at time tk, and it's at time tk we're going to be doing this sort of cycle of observation and so on, right? This observation and assimilation cycle. So you come in here with a forecast from a previous time step, right? Which I'll call xfk, right? You were at t equals tk minus 1, right? And then this process here is going to spit out something else, which we call the analysis, XAK. And you then go on to do a prediction at time tk plus 1. And when you get data available there, you would assimilate that, incorporate it, and so on, right? So this is describing this step here. And this is the specs of what I'll call it. I'll say the forecast at time tk is xfk. The analysis, the thing that we're trying to get out of it, is xak. And the observations at tk are y0k. So our observations here that we're going to be assimilating are y0k. So that's actually not 0, that's O for observations at time k. But the thing is, if you're going to sort of weigh up, you know, you've got this information which has come from the model and maybe previous assimilations, and you've got this information which is the observations, and you've got to make a decision about, you know, which of these you're going to trust more and how you're going to balance these two things off against each other. So generally that's done by assigning some kind of error covariance to each of them. Okay? So we usually call the error covariance of this B. This is the forecast error covariance. B actually stands for background, which is sort of a historical anomaly, I think. So it really is the forecast, but it's sort of the way the variational method, which I'll describe in just a second, is encoded that this was called the background. And then this will have an error covariance R. That's the observation error covariance. Okay, so those are matrices that tell you basically how confident you are in those two different things. Okay, so the three different perspectives are the following. First of all, there's an optimization perspective, right? The way I've set things up, I said you're trying to optimize something, so do an optimization, right? So this is usually called the variational method. So you have a cost function, right? And your analysis is going to be the argument of the minimum of that cost function, the place where you minimize that cost function. And then the cost function is basically going to balance these two things. It's going to balance the forecast and the observations. This is the forecast bit here, right? So you're going to take the inner product of x minus the forecast times B inverse, this is for the error covariance, times x minus xfk, right? Plus, now what you've got to do here is you've got to compare the observations with what the model said the observations should be, right? So that's where the observation operator comes in. So you take the difference between the observation operator at x minus the actual observations, and then you weight the whole thing by the observation error covariance. Okay? So that's the variational method. It says minimize that. So at this time step here, you've got all of this information, and you sort of balance these two things out by an optimization procedure. Okay? So it's a very natural thing to do. Well, here's an equally natural thing to do, and that is to do an interpolation, right? To say, okay, well, no, what the answer is going to be is it's going to be take the forecast here and add a bit to it that pushes it in the direction of the observations, okay? So interpolate between the forecast and the observations, okay, and then say that is going to be your answer, right? That sort of interpolation between the two. Well, obviously you've got to figure out what's your sort of weight of the interpolation. You've also got to deal with the fact that these are different dimensions, but that's basically what the Kalman filter does. And the Kalman filter says that what you should do is you should do this with the Kalman gain here being this matrix here. Okay. Now there's only one thing here, is that this is all matrices, so this all has to be linear. I have not said that the observation operator has to be linear, but you have to linearize it to do a common filter. So this H is actually some Jacobian of the observation operator evaluated at the forecast state here. So this is a linear thing. Okay? And you can prove that if H is linear back here in the variational method, then the XAK that actually minimizes this is given by this formula. Right? So that connects the two strategies. But it's a different perspective here from saying try to minimize this thing here. The perspective is try to interpolate between these two things. Okay? So it's kind of a different way of thinking about it. The third way of thinking about it is in terms of conditional probability, which is Bayes' theorem. Okay? So this is the way a statistician would look at it, because a statistician would say, you guys are completely crazy here. You're going just after a single answer, right? You're saying that you want a single best answer, but there is no single best answer. There's a probability distribution of answers. And so what you have to get is you have to get a PDF, right? And what is the probability distribution function? Well, it's given by the law of conditional probability, right? So it says that what you're looking for here is the so-called posterior probability of the state of the system given observations, right? And your idea is that you're coming into that with some kind of prior probability, which is basically coming from your model here. And you're going to multiply that by an observational likelihood, which is the likelihood that you would get those observations given that state of the system. Okay? So the posterior probability is proportional to this, and you can work out the proportionality constant, and that's Bayes' theorem. Right, the connection between everything is that if everything is Gaussian here, right, which happens when everything is linear, the observation operator is linear. If everything is Gaussian here, then your mode, which is equal to the mean, is exactly given by this analysis, which is given by this formula here. The other connection is that these elements of the cost function here are the log posteriors of these two pieces. So there's sort of a connection between this formula here and Bayes' formula. But Bayes' formula is kind of it's kind of an envelope for the whole thing of data assimilation. Yeah, Mel? Yeah.
Chris, we talked about this, I think, a little bit at lunch. I was talking about something related. And just, I probably should not start talking now because I haven't formulated it as well as I can. I'm taking hidden Markov model. And
Right, right.
If you're given all
Right.
the observations at once,
Right, right.
which you typically
Right.
not always know. But suppose someone saw all these observations and
Right,
wanted
right.
to then
Right.
over a period of time and then
Right.
wanted to
Right.
reconstruct what
Right.
occurred.
Right.
Are you creeping up on HMM, which of course is
Yeah, no, you are. There are strong connections with HMM, but you are, so as I said, my bias is towards data assimilation in sequential mode. In other words, taking observations as they come and incorporating them, which is a somewhat different strategy from taking all of the observations at once, which smooths as well as filters.
So I was just thinking,
But
I mean, could you justify it if someone said, okay, these were the observations 2 years ago, this period of time, tell me what the corresponding weather was, which would be something like the daily state.
Right. No, that's right. So that's in this game they call that a reanalysis. Right. Okay, let's start to look at a specific problem here. So what I want to do next is kind of give you an idea of what the big issue is in data assimilation. What is the big challenge? And this is the Gulf of Mexico, right? And the main thing that's going on in the Gulf of Mexico is the spawning of these rings here, right? So this is actually sea surface height, but you could think of that as corresponding to sea surface temperature. This is based on a Navy layered ocean model, and this is from 2006. You can see the dates here, right? There was great interest in 2006 of these rings because it was the year after Katrina, and Katrina was so powerful because it passed over one of these rings here. If those of you who were around and old enough to remember, right, Katrina was actually a Category 1 storm when it crossed Florida, and it was a Category 5 storm when it hit Louisiana and Mississippi, right? And it turned so quickly, it magnified its strength so quickly because it passed over one of these big warm core rings, and that was the source of the energy from the ocean. But generally, you can sort of see that what is interesting in the Gulf are those eddies, those features. All right. So keep that in mind. What you would want a data assimilation strategy to successfully do is reproduce that kind of information, right? To reproduce those sort of effects. These are actually, I mean, another way to look at this is these are hurricanes inside the ocean, right? So that's sort of physically, in terms of the equations, that's a bit what they're like. So what's the source of data? Well, this is one source of data. Getting data inside the ocean is tricky. You can get satellite data on the surface of the ocean and sea surface height and sea surface temperature with some qualifications about the days being cloudy and so on, and you only get tracks and so on. But getting information from inside the ocean is really difficult, right? Because it's opaque to all of the sort of infrared, microwave, and so on, whatever's involved in measurements for satellites. Right? So this has been a great challenge. This was a very traditional way of doing it, using what were called floats. And this was maybe the state of the art back in the 80s and 90s. And you can see what they would do is they'd drop these instruments in. They're about 2 meters long, so they're about the size of a person. And they would drop them into the ocean, and they'd be pressured to stay at a certain depth, and they would be moving along. And they would actually, what they did was put pingers in the ocean, which would allow these things to encode their own position through triangulation, through sonar triangulation of various strategically placed pinging instruments in the ocean. So these things would float around, and they would actually keep track of where they were. They would then surface after so many months, 6 to 9 months, and they would dump all their information to satellites, right? So these are kind of neat instruments. They could also, in some, they would, now if they were done, I don't know how much people do these anymore, but if they were done, they'd be able to also take temperature measurements and stuff like that. You may have heard of Argo floats, which are a kind of modern, more recent version of this type of thing, but Lagrangian purists, or we say, don't like those so much because they don't stay down there. They come to the surface every 10 days, and that compromises their Lagrangian integrity. So they're not actually following the fluid because they're surfacing every so often. Anyway, we set about deciding how much information do you need, right? How much of this sort of Lagrangian type information of watching these things move around in the ocean do you need to recapture an eddy? Okay, so this was a problem we sort of set ourselves to do. So here was the idea. Here was one of these eddies. This was generated now. This is from our numerical model, which was the one that I showed the grid for that Guillaume Vernier did. Right? And this was an eddy that spun off. It was actually about the simplest model that had eddies within it, these kinds of ocean eddies within it. And we thought these are following fluid particle trajectories around here. Now suppose you didn't know this eddy was there, but you knew these trajectories were going around and around like that. Could you somehow reconstruct that eddy using data assimilation? That was sort of the test. And this was work with Guillaume Vernier. Well, he was at NASA then. He's now at NOAA. Kaio Ide, who's at Maryland, And this is what we got. So let me explain it. This is the control run. So this is the run where we actually have that eddy. We have this sort of ring, this eddy detaching from this. This is called the loop current. It's part of the Gulf Stream going around Cuba and out the Florida Straits. And this detached from that, and the question was, could we capture that? All right, and there were 3 different experiments here. Both of these experiments were different types of Lagrangian experiments. That is that we put these fluid particle trajectories in, and we allowed ourselves the information that those fluid particle trajectories were at certain places at certain times, and we used that information in data assimilation to put into the model. Now what we did is we did what we called an Eulerian data assimilation, where we said, okay, what we know is the velocity at certain points where the eddy passes over. Is that enough? Then that's a comparison with putting these Lagrangian observations in. And you can see that the Eulerian data assimilation really isn't enough to capture the eddy. It does kind of, but these Lagrangian assimilations really capture it well. What we had done, initialized these with, is basically this control run without any eddy, right? So we killed the eddy, and the question is, can we pull it back? Can we reconstruct it by assimilating this kind of information of these trajectories? Yeah, Bill?
Quick question. I explained it. I may have missed it. The difference between an Eulerian approach and a Lagrangian approach.
All right, so the Eulerian approach is so that if you look at an Eulerian formulation of a fluid problem, you're basically looking at all of the physical quantities as time varies with a fixed view of space. If you take a Lagrangian view, the Lagrangian view says you watch a fluid particle and you look at how the properties change as that fluid particle moves along. In this case, all I really mean is that here we're looking at fluid particles that move along, and here we're looking at fixed stations, right? In terms of the data, that's just observations, right? So here it's like our observational platform is moving with the flow, and here it isn't. Okay. I mean, we were interested in Lagrangian data assimilation generally because the type of data that you get subsurface tends to be Lagrangian, because you put stuff down there and you let it move around with the flow. So it tends to be Lagrangian, and we wanted to see how good is that information as a source of observations for then assimilating into the model. Okay.
So there's an interplay between the surface height, and then the temperature that's being, associated with that buoy system underneath. And can you revisit that?
Yeah, that's right. That's kind of geostrophic balance. If the natural limit for a geophysical fluid is geostrophic balance, where you have Coriolis balancing horizontal pressure gradients, and that from that you can conclude a relationship between sea surface height and stuff that is then going on underneath the surface. But you're right, that hides an awful lot. So I mean, that was sort of one of our questions in a way, is if you don't necessarily know that it's behaving in that way, but you have this information that these things are swirling around underneath here, is that enough to recapture this key phenomenon of the eddy?
So,
yeah,
on the other slide, the control, you might have mentioned this, or this might be an ocean thing. The eddy, the control one.
Yeah, here.
Yeah, I have confidence that that's simulated. So
that's simulated, yeah. Right, so this is
a real eddy behaves like
right.
Is
well,
the target the right target?
yeah, so I mean that's a good question. So what we tend to do in data assimilation is we tend to do what's called identical twin experiments, and it's because the world is sort of just a little bit beyond our reach, and we want to do a lot of testing of ideas and methods, right? So we test those ideas and methods against a control run. So we say we're pretending that this particular computation is the real world, right? We then make some kind of an error, right? And we see, can we correct that error by making observations? So the error we correct, the error we put in here is kill the eddy, right? Can we correct it then by incorporating observations? Will the model, together with that observation, put us back on track and get close to here? Right? We're not really claiming, we're really testing the data assimilation scheme. We're not really claiming that we're understanding a physical phenomenon. Okay? Okay, so let's go back to talking about, what I want to talk about now is really what is the real core issue in data assimilation? What's the big challenge that is driving the area? So remember, this is the DA setup. Right? This is data assimilation in sequential mode, right? Where we go to a certain time and we go through this assimilation cycle, right? And these are our three different perspectives, the variational method, the Kalman filter, and Bayes' theorem, right? And they're all sort of intertwined with each other, but if you come from one of these camps, you tend to look at the problem in a certain way, okay? There's a lot of kind of historical culture behind each of these perspectives. Okay, so that's the whole DA setup. Now, why don't we just say, you know, Bayes' theorem is kind of the be-all and end-all, because it actually gives us PDFs of which these analysis things are actually modes or means or whatever. So this contains the most information. So why don't we just calculate these PDFs, right? Well, you heard in a talk this morning about how difficult it is to calculate those PDFs. That's what sort of sampling. And here's kind of a sort of background in why this is such a challenge. Because what you would do naturally is you would try to evolve your PDF under the model. How are you going to get that prior PDF, right? You're going to evolve it basically from some previous PDF, the posterior of the previous time step. To do that, you use the Fokker-Planck equation, which is a partial differential equation that tells you how to get from some probability distribution time t0 to time t1. This is your model here, okay? This is some you know, one of the components of the model. This is noise that you put in, and this is the Fokker-Planck equation, and it tells you basically how you get from some PDF here to some evolved PDF. So this is the point at which you're going to do data assimilation. This is your PDF at the previous time step. It says this is your sort of belief in the state of the system. So let's say the state of the system is actually here. This is the real world, and it's evolving in a very messy way up to here. This is your best guess estimate. This is your best guess estimate under the model, right? Okay. And then what you do is you do, Bayes' theorem says, well, what you do is you have a partial observation. So I'm assuming my system here is two-dimensional. So here this cartoon says the partial observation is I observe one of the two variables, right? So I got some PDF of the observation here. I now kind of multiply these two things in Bayes' theorem and I get a new PDF, okay? Well, that looks great. The only thing is this step here, this evolving the PDF here, right, is extremely difficult. This is the Bayes step. This is sort of okay, the actual Bayes step, provided you have these PDFs. But how do you get these PDFs here? Well, if you think about it, this has independent variables xi. They're written as xi to sort of make it look like they're spatial variables, but they're not really spatial variables. They're actually the state of the system, right? Now, our state of the system may be as much as 1 million dimensional, or even more. Now in current atmosphere, ocean, climate models, maybe 10 to the 9 or even more, okay? So that means that this is a partial differential equation in 10 to the 9 independent variables, right? These start getting difficult to solve when you go to 3 or 4, right? All right, so this is sort of, so thinking of Bayes' theorem as solving data assimilation is like saying fluid mechanics was solved when the Navier-Stokes equations were written down, right? It was the beginning and not the end. Okay, so how is it actually dealt with? Well, there are 2 dominant methods, I would say, from the sort of development academic point of view. It's true that operational centers will tend to use the variational methods, but the people developing data assimilation tend to use one of 2 methods, the ensemble Kalman filter or the particle filter. So let me explain each of these a little bit and explain to you their shortcomings, and then you'll see what the real conundrum is in data assimilation. So the ensemble Kalman filter basically says take the Kalman filter equation. So you take this interpolation point of view, right? And we're going to come up with a neat way of coming up with this matrix, Kalman gain matrix. Okay, that's kind of the game. We're going to come up with a really neat way of getting this thing here. The original Kalman formula involves kind of linearizing everything and assuming everything is Gaussian. We're going to release ourselves from that constraint a bit. The particle filter says we're going to use Bayes' theorem, but what we're going to do is come up with sort of ways of getting sampling approximations to these PDFs. Okay, and there's a close similarity between these 2 approaches. Here what we do is we base things around ensemble members. Okay, so you start out with a kind of a guess, but you don't just make one guess, you make a bunch of guesses. You're like a spray of guesses. Could be centered around a particular guess. But okay, so over here we're going to have what are called particles. Okay, so these are very like the ensemble members. It's a spray of things, but these are going to have weights to them. They're going to have, say, some of them we're going to say are more important than others. They're weightier than other ones. Okay, here they're all the same weight. Okay. Okay, so this, what we do is we take the ensemble members and we evolve them under the model. I'm going to draw a picture of this in just a second. Okay, but just remember that. Here we evolve them under the model, but we usually put in some additive noise. So you evolve them under the model with some white noise. That sort of jitters them. Okay, but other than that, they're basically evolved under the model. Right here, we're going to recreate a covariance matrix from this ensemble. Okay, so this KK, if you remember, we had to write out this complicated formula. But we had to have this sort of background error covariance matrix and observation error covariance matrix and so on. We're going to actually use our ensemble members that have evolved under the nonlinear system to create that covariance. All right. Here we're going to evolve the particles from the prior. So we just evolve them from the prior, and we've just got a new spray of particles. Okay, and that's sort of forming the basis of our PDF, of our prior PDF. Yeah.
Just to check the weights get incorporated into the prior? And
No, they don't get incorporated into the prior. I mean, you may. I mean, there are different ways to do it, but you may start with weights from the previous step and carry those weights through. Or very often what's done is you jitter those apart so everything has an equal weight, and then you let those forward, and the number of ones you jitter apart depend on their weight. But no, so I'll explain that in a second. But basically you just take these particles and evolve them. Okay, and and the PDF is basically then just your sort of sample approximation. In other words, it's a sum of delta functions, right? And that's approximating your PDF. It's like a histogram, right? All right, so here you update the ensemble using the Kalman filter with K based on this covariance matrix, right? Here what you do is you reweight the particles by distance from the observations. So this is where the weights come in. So it's it's very clever, right? This particle filter, and it's a different way of doing things, but there's a relationship. Here you actually have a new ensemble because you move them around. Here you do not move them around. You do not have a new ensemble, okay? But what you do is you create a new PDF because of the weightings. In other words, you have a sum of multiples of delta functions where you have the weights in there. All right, let me draw a picture of the two different things. This sort of explains it. The ensemble Kalman filter, you start off with a spray, you run the model, right? So this is going from this step here to this step here, right? And you're trying to create a sort of error covariance at this step here, a confidence in your forecast, okay? So you take your spray here and you evolve them down to here, okay? So each of them has sort of moved. Now, what you're going to do is you're going to take each of them and apply a common formula to it, where you've created a covariance matrix based on this sort of spray of ensemble members. So you're going to move these here using the common formula, okay? You're going to move them towards the observation. So that gives you a sort of a new spray, right, where you move them according to the observation. Okay, so the particle filter says you start off here, but some are more important than others. They've got different weights, okay? You evolve those, they keep those weights, at least that's one way of doing it, right? They keep those weights, right? But then what you're going to do is you're going to say, look, this guy here is that's a heavy weight, right? But he's quite far from the observations. So I'm going to reduce his weight because he's too far away from the observations and make it a small weight. And these ones here that were close to the observations, I'm going to give them greater weight. So you're pushing the PDF up there if it's near the observations. And this is the assimilation time step, right? And you can derive this. This is sort of consistent with Bayes' formula, right, in a sort of discrete sampling approximation. But these are two very different ways of looking at the problem, but both use this sort of underlying evolution of the model to get to the prior, okay? Right, so these, I think, are the two sort of approaches that really underpin most research in data assimilation right now, most academic research anyway. The problem here is with nonlinearity. The problem here is with dimension, right? So this does not do terribly well with highly nonlinear problems, and this is challenged when it goes to very high dimensional problems, okay? And if you think about, the sort of the weather, climate, atmosphere, ocean, and so on, they are both very high dimensional, right? 10 to the 6, 10 to the 9, and there are also nonlinearities in them. The basic fluid equations are nonlinear because they have these advection terms, right? Navier-Stokes is a nonlinear equation, right? It looks simple, the nonlinearity, but it isn't. So you've got those two aspects, and you've got two methods, one which does one well for one of the aspects and another does well for the other, right? This deals with nonlinearity. I mean, this is perhaps oversimplifying a bit, but this deals with nonlinearity and this deals with dimension pretty well, but neither with both, okay? Let me explain a little bit what can happen with the ensemble Kalman filter and what can happen with the particle filter. This is called filter divergence, right, where things go wrong. So the problem with the ensemble Kalman filter is that basically what you do is your Kalman filter just pushes you towards the observations. Now, what if you happen to know that in the model space there was no way that you should be in here? Right? So something in the physics says there's no way you should be in here. There's like maybe a hole in the phase space, right? You shouldn't be in here, but the Kalman filter, because it's just this linear interpolation, is going to push all of these things into the no-go area, right? Which is problematic, right? So that's sort of what happens here. If the nonlinear system has a hole, but the linear assimilation step puts the ensemble members in this no-go area, that's obviously kind of a problem. Now what happens with the particle filter? What happens with the particle filter is that they can actually all sort of bunch together. And if you look at a very high dimensional problem, you know it's to do with this issue that if you go to very high dimensions, sort of spheres or balls in very high dimension are actually have their mass concentrated in a very small area. Right? It's one of these sort of ironies of high-dimensional geometry. It's kind of mind-bending if you think about it. But its manifestation here is that what can happen is all of these things can look like they're very close together, right? And if so many of them are very close together and they're all sort of near the weight, then they all get weighted too much, right? Or what might happen is just one of them gets near and the rest are too far away and they get no weight at all. So you end up with sort of basically like a sort of single delta function in your particles. That's kind of what happens here. So the particles can collapse into a small region, especially in high dimensions, and you can end up with essentially a delta function PDF. So that's the sort of problem over here. So the sort of deep conundrum is nonlinearity versus dimension. This was actually where we sort of discovered this effect with the ensemble Kalman filter, where we had this was a cellular flow field and we had trajectories going around a center here, and we saw that if you did the ensemble Kalman filter up to a certain observation set, so it depends on how frequently you observe. If you observe very frequently, you can do anything, right? But you don't necessarily observe frequently. We do have no control over how often we observe relative to the timescales of the system, right? So, and this was an observation set where you weren't observing very much. This is a sort of statistical type method. It's actually a modified Lagrangian sampling method. And then this is an ensemble Kalman filter method, and basically this just sort of gave us a flat PDF, right, virtually. And this was, we took the observation set and said observe further and further and see if it gets better, and actually it didn't. So this is kind of a picture that shows you a little bit about what's going on, because you end up with your prior PDF looking like a donut, right? And essentially, if you think about the ensemble Kalman filter, it's like trying to take a Gaussian approximation to that. What's the Gaussian approximation going to do? It's going to have its mean right here, right? But nothing's there. So, okay, so that was sort of that was the problem there. All right, just to sort of finish up, I just want to give an idea of our perspective on how we resolve this. Well, we noticed from Lagrangian data assimilation, the way we do Lagrangian data assimilation is that basically we augment the system of equations to include equations for these drifters that go around, right? So we had flow equations and drifter equations, right? And we're observing this and we're trying to estimate this. So this is kind of an artificial extension of the system, because this is information is somehow included in here, but to do the data assimilation, it was a smart thing to do to augment the system. It's a standard strategy. But that gave us a sort of dynamics that had this kind of intrinsic Skew-Product structure, right? Where we had piece of the model here, and this is the model and this is the observation operator. The model split into two pieces, right? There was one piece here and one piece here, and this was somehow dependent on this, but not vice versa. That's called in dynamical systems a Skew-Product structure. Okay, and you can exploit that. And our idea was, well, okay, you've got maybe one of the parts is high dimensional, one is low dimensional. Try to use the ensemble Kalman filter on the high dimensional part and the particle filter on the low dimensional part. Right? That's a great idea, but it's easier said than done. Actually implementing that is quite tricky. This is roughly kind of the setup here. This is the continuous version. This is the discrete version, right? You're trying to estimate the high and observe the low. And this was, and do the NKF on this and the particle filter on this. And we call it, it's called the hybrid filter. And this was actually realized by Slavinsky, who was a student at Brown of Bjorn Sundstede from our old department. Elaine Spiller, who was the person that Rudy Horn introduced me to. He had been her TA in Colorado. And she is now, I think, one of the best people working in data assimilation. And Amit Apte, who's my former postdoc and colleague in India. Anyway, they came up with this and it was very successful. Just to end, let me say though that, you know, we've gone in a way, we did think of this with these floats that they were putting in like the 80s and 90s as a small data problem. But now they put in these drifters, and these drifters sort of sit under the surface of the ocean, and they can put in loads and loads of them, right? They're sort of much easier to put in, and they have an expression here which allows them to communicate with the satellite. It gets only near surface information, but there's a lot more. So I think there's sort of an evolution of this Lagrangian data assimilation from having a small number of floats, which give us sparse data, to really having a large number of these so-called drifters, which are sort of different instruments, which is giving us a big data problem, right? So we're moving from a sparse data problem to a big data problem, right? Now, why is that so important for data assimilation? It's important because it's really the dimension of the observation space that matters, because that's where you're comparing things. You're comparing how well would the model, is the model doing in predicting the observations, and comparing them against real observations. And if that's high dimensional, that's what's going to cause problems for the particle filter, right? So the particle filter will inevitably collapse in that. So this is why I think this kind of hybrid filter sort of idea is so critical. We've actually applied this idea in a number of different ways now, this kind of hybrid idea, and I'm not going to go through this now, but we did it in coherent SOCA. We developed this coherent structure data assimilation. I want to get to just one point here, which has a historical reference in a sec. And then we applied it to parameter estimation, which also has this Skew-Product structure. Here you observe the high dimensional and estimate the low dimensional. In some ways it doesn't matter very much which you do, which is high and which is low, as long as there's a separation into high and low, and then you can start developing these hybrid filters. So we do a hybrid filter in this case here, right? And this is rather a complicated diagram which explains it all. Sorry, I don't have time, but I want to mention that this is essentially a Rao-Blackwell filter, okay? And Blackwell was, I think, you know, one of the eminent African-American mathematicians, scientists of the 20th century, right? And one particular reference here is that in 2006, Bill Massey won the Blackwell-Tapia Prize, and it was at IMA that it was awarded, and Blackwell could not be there. He was elderly at the time, and in fact he died in 2010, and we held a meeting. I was running then a special semester at MSRI, the Math Sciences Research Institute in Berkeley. David Blackwell was at Berkeley, right? And we ran a small meeting there in the spring of 2007, and Rudy came and Bill came, and Jelani was there, and we had a dinner where Blackwell came along and could meet the current recipient of the Blackwell-Tapia Prize. Well, you probably already knew him, but we were able to celebrate that. anyway, and it was a great thrill for me to meet him, but we had no idea a few years later that we would basically be basing all this work on the Rao Blackwell filter. So, all right, this was just, I just want to go to the end now. So back to the sort of original question in a way, which is about this fundamental tension in data assimilation between nonlinearity and dimension. And the method of ENKF is rooted in the sort of dynamical idea of evolving a spray of initial points in phase space. It's a very natural idea from the dynamical systems point of view. And we know that the breakdown of ENKF is due to known dynamical effects, like this shear, right? Which is what causes you to get this donut-shaped PDF that we saw. Much of the current work in addressing the particle filter breakdown is statistical in nature, which is great. It's intended to work universally, but their idea is that they want to just keep refining the particle filter to work in higher and higher dimensions. The problem is that computers keep getting ahead of them, right? So if they get to a certain point where they can make the particle filter work, they wake up the next day and actually we've added 10 to the 3 in the resolution and in the dimensions of the phase space. So my fundamental belief is that we have to look for this splitting between high and low dimensions and develop these hybrid filters, right? So, and this is to use the dynamical understanding of the models to get this low dimensional phase space. All right, that was it, I guess. Yeah. All right, thank you.